record, so I'm starting recording a little early, like a minute. So if you want to start copying that down. This is the essence of what we're doing today, which is section 4.1. We're really looking at just the first derivative and what that graph looks like. And then we're going to talk about finding the partition points. At least that's the first 6 to 7 examples that I hope to cover. If I get beyond that, like I said, super, but I'm more concerned about making sure you understand what's going on and that you feel comfortable with what I'm talking about. In this first example 1, I'm talking about finding intervals on which a function is increasing or decreasing. So if you notice, the function that they give us, the f of x, the original displacement function, is 8x minus x squared. So the first thing you're going to want to do is we're going to want to take the first derivative. So if I take and I differentiate this, I'm going to get 8 minus 2x equals 0, which means that I technically can factor out a common term. If I factor out a 2 from here, I end up with 4 minus x, which means since that's equal to 0, I have a repeating 0 and I have x equal to 4. Okay, and that's the first step that you're going to want to take. So that answers right here, that answers that point. What makes this 0 and what gives us height? What gives us a tangent line? And that's what we get. The next question is saying, for what values of x is f of x increasing or decreasing? And that's where Desmos comes in. Notice they talk about f of x. So what we're going to do is we're going to go to Desmos. Okay, and then what I'm going to do here is we're going to graph f of x is equal to 8x minus x squared. If you notice, this is what you get. Basically a parabola. If you notice the values here, let me see if I can pinch this in just a little bit. So the value here at x equals 4 is what I'm interested in. And this is what I need you to understand. We read these parabolas left to right. So if I'm reading this left to right, I'm coming from the negative values up to the parabola itself. And left to right, which direction are the points heading? Positive or are they negative? Are they heading up? They're heading up. So we would say that in this case, the function is increasing from negative infinity up to 4, not inclusive. And then from 4 to positive infinity, what's happening? Decreasing. And that's what we're looking at in terms of this. So this answers part B of the question, which is basically asking for which values of x is the function f of x increasing or decreasing. We would say negative infinity comma 4 union, and again we would consider from 4 comma infinity, and that would answer our question. So we know it's increasing here. I'm just going to put an arrow for increasing, and then is decreasing on the other side. You should use what they refer to as test points. So for the record, I know we were asked to sketch it, which you're welcome to do so. I mean, technically this is your xy plane. Here at 1, 2, 3, and 4. At 4 we have an axis of symmetry. And this is obviously at the tangent line. It's when you look at the graph, you can see, get back to Desmos. We're at this point here, which is the point 416. So that'll help us graph that point. And then here it looks like it goes through 0, 0, obviously. and the other point here, 8, 0. So those key points can help us graph if we're doing it by hand. So then the points that are mattered to us, 0, 0, 5, 6, 7, 8 is another point that's important, and we're assuming this point up here is that vertex. So obviously growing in this direction. One more time, if I choose a test point and say hypothetically anything here is a test point that I can choose, I could choose the -1, or actually this would be 3, 2, 1, 0. I would not want 0. Here, this would be 5, 6, 7. And so you would choose points such as that. And if you have x, and then here's your f prime x value, we would choose, like I said, we could choose 3. So if I choose 3 as a test point, I throw it into the equation, I get a result of 2, which is positive, meaning that it's increasing. If I chose the 5 instead, then I notice that I get a -2, and this is obviously negative. So go back to your f prime x equation, your first derivative equation, where we would say, for example, f of 3 is equal to 8 minus 2 times 3, and f of 5, when this is going to equal 8 minus 2 times 5, hence the results as you see here, which are +2 and -2, which tells you whether these functions are increasing or decreasing. Once again, left to right, what's going on? Left to right on this side of the 4, it's increasing. Left to right on this side of the 4, the function is decreasing. Okay, so remember, this is -infinity over here. This is -infinity over here. Reaching up to the top, from the top down. So that first derivative will help you. And so, yeah, we would state that, just as I wrote over here, that the f of x is increasing from -infinity to 4 and decreasing to 4 to negative or positive infinity. Questions on this one? What questions would you have? Any questions? No questions?
So that, I don't know what they call it, but the negative infinity of 4.
The interval.
Yeah, the interval. How come on the right side it's to negative infinity when it's positive infinity when it's going down?
Remember, these are x values.
X? Oh.
Yeah. So maybe make a note to yourself, and these are little glitches that I need you guys to clarify so that you don't have issues. Remember, these are only the domain.
Okay.
So I would just put x's or the domain. So when I'm talking negative infinity, I'm coming this way, going in this way, which basically left to right, I'm still going up. And then, because remember, the up and down is relative to y, relative to y, or f of x. And this is positive infinity here. So keep that in mind. Do you want to try one of these on your own? Yes? No? Give me a nod for yes. Okay. So I've got several yeses. So same concept, same questions. I'm going to give you same concept, same questions. And I'm going to give you the following question. So I'm changing this. Obviously, I'll get rid of this. So you can just write down the function and figure it out from there if you wish. I'm just going to erase all of this to not cause you confusion. All right, and that is, here's your function, your try question. So this would be f of x is equal to, it's equal to, take that back. X squared minus 6x plus 10. I can give that a shot. All right, so your first step here would be to find that derivative. And this gives us a derivative of what?
2x minus 6 equals 0.
Okay, wonderful. And now what's the next step?
Factor out the 2.
So x minus 3 equals 0. So what's the partition number we're talking about here?
X equals 3.
Yeah, so x equals 3. If you, once again, go to Desmos, you want to graph this out. So this gives us x squared minus 6x and plus 10. And that's what it looks like. I'm going to erase this. Actually, no, I'm going to change it to 3. Right, because it's positive x squared. It should be facing up. And so left to right, what are you going to tell me? What's happening? Is it increasing or decreasing?
Decreasing.
It's decreasing on the left. And what's happening on that side?
Increasing on the right.
Yeah. Increasing on the right. So to answer the question, go back here. Keep forgetting I have to hit it. Okay. Yeah, so x equals 3 is our partition. So actually, it didn't change. That's still the same numbers. So I'm looking at this diagram and I'm saying here's x is 3. And that's the partition. And we know that this is going through 10. So let's pretend that 10 is here at the y-intercept. So this is going something like this. Boy, no. It should be touching the x-axis. So let's take a look at what this picture looks like on Desmos. Actually, no, it's correct, the way I drew it. So at 3, 1 is a vertex. Do you know how to find a vertex? Need a refresher? Quick refresher? Okay. So that 3, 1, so let's go back here. We have the first derivative of, actually, the function itself is f of x equals x squared minus 6x plus 10. So if we're drawing this, the vertex or the x value, which is referred to as the axis of symmetry, do you remember that?
Yeah.
Okay. So axis of symmetry, which we use with the original f of x, which is going to be negative b over 2 times a. Now remember, in this function, there is a 1 here. You have a negative 6, that's your negative b, and this is your c term, right? So that's a, that's b, and that's c. So according to this, this is negative of negative 6 divided by 2 times 1. So double negative, that becomes simply 3, which we factored out anyway. And so we know this opens up, and so the 3 is the x value of the coordinate pair of the vertex. So this is your vertex. If you want to find y, plug this back in. So you get 3 squared minus 6 times 3 plus 10. So really, in reality, you have 19 minus 18, hence 1. And that's your vertex. So going back to the diagram, I'm recording this, by the way, for those of you that you notice the vertex is right here, right? So our partition number. So when we look at the diagram, looking at the diagram from this perspective, left to right, this being the cutoff here at x equals 3, from technically negative infinity on the x to 3, we are decreasing because this is going down. And so I'll say union 3 to positive infinity on this side of the x-axis, we are increasing. It's going up. Questions? Issues? No? Okay, so that is that answers our 2 questions, right? The A and B.
Yes.
And we sketched it already on Desmos, so we answered C. Okay, so if you're cool with that, I'm gonna go into the second example, unless you have further questions. No? Okay, example 2. In example 2, we're talking about critical numbers. And so we refer to this as partition numbers for the first derivative. I'm just going to go f prime x. And critical numbers of f. That's what example 2 is dealing with. And they want to find, the first thing they want to find are what are the critical numbers of f on the intervals on which f is increasing and those on which f is decreasing for the function where we have f of x is equal to 1 plus x cubed. So the first thing we're going to do is we're going to take that first derivative. So we're going to find the first derivative, which in this case is simply 3x squared. And therefore, in this case, we just need to solve where x is equal to 0. The partition number 0 for the first derivative. So this is your partition value or number. Sorry for the mess. Where x is equal to 0. So if I look at the graph, I have no idea what just happened. If I look at the graph and I'm looking at 0 and right in the middle, my question is, what is happening with respect to the derivative diagram? So from negative infinity to 0, what's happening? And from 0 to positive infinity, what's happening? And so the f of x tells it all. So let's graph f of x. And we're going to test 2 points. We're going to test the point -1 and +1 to see what happens. So in your notes, what I'd like to see happen is I'd like to see you do a test number t table. And this is x and the value of f prime x. So we're going to look at these two and we're going to pop in -1 and 1 to find that value for f prime x. So I'm going to go to Desmos. Do I need to slow down for a minute?
Yeah.
I can see pens still going. Namely here. You guys are like my hotspot. I'm watching. Is the pen still moving? All right. So I come over here and we're going to change this. I'm going to get rid of this. I'm going to get rid of this. So the f of x, I have 1 minus 3x squared. That's all I have here. So that's my diagram with x right in the middle, right? So here's x equals 0. And then...
Are you graphing the derivative? Or
no, that's the original.
Oh, okay. I thought the original was
so,
x
1 plus x cubed.
It's 1 plus?
No, what? Yeah, 1 plus x cubed.
Okay, so there you are. Regardless, that's the diagram. What drugs am I on? There you go. So when we look at this, this is what the original cubic function looks like. It's an origins function, simple, and it's going straight through 0, 1. We could see that clearly. But that's not the one we're interested in. The one we're interested in is, I'm going to call it g of x, which is really the first derivative, is equal to the 3x squared Again, look at this purplish function here and tell me what you see happening left to right. Where is it increasing? Where is it decreasing? Left to right. It's decreasing on the left. It's going from negative infinity down to 0, and then from 0 up to positive infinity. So let's see. So when x is 1, we are what, about here? So if you look at the graph, this is just looking at the graph. So at negative 1, we're at positive 3. And at positive 1, which is equidistant as well, we're right here, that's also 1, 3. So at that peak, that value, we're positive on both sides. So in that case, this is indicating that it's increasing on negative infinity to 0 and 0 to infinity. So it's going up on both sides. It's strange. I would not interpret that way, because left to right, what is happening here, well, on the derivative, hang on, that's why I drew this one. That's why I drew the original. Look at the red one. On the red, what do you notice? It's increasing on both sides, and that's what they're stating here. And you would find that because you wouldn't answer that based on the purple, right? Left or right on the purple, it's decreasing on the left, increasing on the right. No question. But when you question the behavior of the original graph, it's increasing on both. And you find that from the derivative itself. So let's take a peek at what I mean by that, in case you missed it. So if we test negative 1, our first derivative is 3x squared. So we're going to say 3 times negative 1 squared, which is positive 3. So this is positive 3 plus. If I take that first derivative, well, yet again, obviously this is going to be positive as well, because this is simply 1 squared is equal to 3. That's 3. That's also positive. And that's telling us that the test number, in other words, the sign chart indicates that the f of x, the red function that I originally showed you, is increasing on both sides, left and right. Make sense?
Yeah.
Huh. All right. Okay. If we look at the figure yet again, where am I? If you look at this figure, see right here, this is a 0-1 crossover. It's increasing, it doesn't matter what. It's continuous at x is 0. That's another thing to take a note of. If you notice, it's still continuous there. I know it's tiny, but even though it looks constant, it does hit a pocket of constant. It's just crossing over. All right. Do you want to try one on your own, or are you starting to, is this starting to marinate? Whatever you want. You want to try one or no? Give me a thumbs up if you want to try one.
Yeah.
Huh?
Yeah.
Yes? Okay. All right, so let's do a try. So we're doing the same question. I'm going to leave this up on the board, and I'm going to do this on purple. Call it try. And then this one, I'm going to give you, I hate that they give you such a basic number, but let's start. Sometimes the basic is not so basic. All right, so try that one. Find the critical numbers of f on the intervals on which f is increasing and those on which f is decreasing. This is the original direction. I forgot to write the second part in purple. You can add that. Is there any partition where you think this original equation would not be decreasing?
But the behavior of the x cubed?
By the behavior of the original f of x?
No.
I think this is decreasing on all areas. So it's decreasing on both areas or both sides of the partition. So let's talk about this for a minute. So this one is simply 1 minus x cubed. That's what it looks like. If I were to differentiate that, I would get negative 3x squared. Do you see why we would say it's decreasing on both the left and the right? Yeah, because the negative flips the cubic function over, and therefore left to right it's going down and it keeps going down. So if I were to look and say this is g of x is equal to negative 3x squared, what do you notice? It's going to go down. It's a sad face parabola, as we jokingly call it. All right, so even if you selected a test point, pick a point. Give me one.
-1.
Okay, so -1, we're here. What do you notice? And here at -1, where am I? I'm also negative. Because we use the derivative, right? The derivative tells us what's happening. Do you notice they're both negative?
Yeah.
And if I do, let's do this one. Looks like it's, so this is x is 0.58. I'm still negative. It's going down. That first derivative is your tell-all. This is telling you, hey, got news for you. Left to right, this is going down. So is this. You know how you could tell? Look at my numbers. Negative, negative. Negative, negative. The y values are negative on both sides. See? Positive, negative. The y is telling you, hey, I'm negative. Okay? So far, marinating?
Yeah.
Okay. Let's look at example 3 then. All right. Example 3. I can't wait for Santa to bring me a new laptop and a power drill. So I'm dying for a power drill. Go figure. Okay, so again, this is partition. Partition numbers. For f, the first derivative, and critical numbers. It's the same thing we did. For f of x. Okay, and this time we're going to use technically chain rule. So they're giving us f of x is equal to 1 minus x to the 1/3. Do you remember these? You can differentiate them pretty quick. So take the first derivative of this. You can understand now why I took a pause on chapter 3. So we have 1/3. If you start it the long way, you have 1/3 times 1 minus x. This is raised to the negative 2/3, and that is times -1. Okay, so I'm doing it by steps so you can follow. You follow why the lunacies. So this is now -1/3 parentheses. Well, you know what? Technically, I could bring it down. Let me just do that. So -1/3 parentheses x 1 minus x to the positive 1 minus x to the positive 2/3. And that's your first derivative, and that's what you're looking for. So if we draw it, let's draw the original. So technically in this case, so -1 divided by 3 parentheses, where did I write that?
1 minus x.
Yeah. I'm just looking through my notes real quick. There's something I wrote to myself. Oh yeah. So yeah, so 1/3 parentheses 1 minus x, and I'm raising that. I'm gonna do parentheses 2/3. Okay, this looks like a mess. Okay, and I don't need this. That's the f of x. Or actually the original, the derivative itself, then red. The original equation, which is 1 minus x, and this is raised um 1/3. Yeah, I just want to make sure I don't mess it up. What do you see? What's my cutout number there?
1,
Yeah. So what would be a good test number?
2,
And
0.
and 0. Yeah. Because at x equals 1,
You get
that's the cutoff. I'm thinking that 0 and 2 would be good test numbers. Left to right, what is happening?
it's going up. Or it's going to the left.
It's
going up.
decreasing. I think it's decreasing on both sides.
Yeah.
I think it's decreasing on both sides. Forget about this one for a minute. We'll use that mathematically. Let's just delete that. Delete this. Going back to the original. All right, what do you think? Left to right, what's happening? Decreasing from -infinity to that 1, and union 1. Do you see why I say it's decreasing?
Yeah.
And if we tested the numbers mathematically with the derivative, we would take, so here's the x values, and I said use 0 and 2. Those are your two values to use. And I said, okay, well, this results in -1/3. And this also results in -1/3. And both of these are decreasing on that derivative, right? Because remember, this is your f prime x value. And so looking at the value, we know that this went like this, with the partition at 1, at x equals 1. That's why we used the 0 at one point, and we used the 2. Okay? So decreasing, this is decreasing here, and it's decreasing here, and it's proven by that first derivative substitution. How do you feel? You want to try one on your own, or you want to move on? Try one on your own or move on? Yes, try one?
Yeah.
Okay. Okay, I'll leave this one up here. I'm going to give you this in purple. So we're going to try. And please do the first derivative test, which is right here. So you have to find the first derivative, select your partition number, and then do the test. And so I'm going to give you f of x is equal to 1 plus x raised to the 1/3. All right, give that a shot. So you're trying this one right here. So looking at this without any more math, just look at the picture. Is it increasing? Both sides?
Yeah.
I would argue yes. And would you say then that first derivative, once you take it, that -1 should be your critical cutoff?
Yes.
Yeah. Did you do the t-test or the t for the points? Right. Let's take a look. So if I'm going to follow this model that I see here, based on the fact that -1 is my partition, so I'm going to actually even erase this to not confuse anybody. So if we take that first derivative for this should give us -1 over x minus 2 squared. Do we agree? I'm in the wrong question. Lovely. So this will give us 1/3 as we start, and 1/3 parentheses 1 plus x. Huh? -2 over 3, and this is times obviously 1, so big deal. So it's really 1 over 3 parentheses 1 plus x to the 2/3.
Wouldn't it be -1? 1 squared by -1?
Where's the negative? If I take the first derivative in here, it's positive, right?
Okay.
So it doesn't really matter. Yeah. All right, so what 2 points did you use? -2 and 0. Okay. And so, is this increasing or decreasing on the derivative? If I plug in negative, you know what, let's plug in 0, start with 0. 1 to the 2/3 times 3 regardless is positive, yes?
Yes.
And negative 2, if I put a negative 2 in here, I'm going to end up squaring it anyway.
Right.
It's still going to be positive. I don't care about the number right now. So it's increasing on both sides. And we see it because the diagram is also increasing. It's actually going like this. With a partition at x equals -1, right? All right. Ready for number 4?
Yeah.
All right.
Question.
Yeah.
Without graphing it, we're finding the partition by finding the tangent.
The horizontal tangent. Mhm. Right. In example 4, we're looking for the partition number. So same thing. Partition number for the first derivative. And the critical number on which f is increasing or decreasing. Can I just put arrows? Increasing or decreasing? So in this example, the function they give us is f of x is equal to 1 over x minus 2. All right, so we find the first derivative. This is going to be -1 over x minus 2 squared. Do you notice that 2 is not a valid value to use? And why? Do you think so? Yeah, look what happens when I graph this. Let's take a look. So please, when you do this chapter, take a moment and just, I know some of you probably are losing their patience with my graphing, but there's a reason I'm graphing and giving you the visual. There's a reason, because it's tied directly to this assignment. So notice that at x equals 2, what happens? Yeah. So in this case, it's not defined. We can't use that. But if you look at the figure left to right, what's happening? Look, decreasing left to right on the left, and on the right, what's it doing? Also decreasing. So it's decreasing on both sides. And we could use a test point to see it if it's true based on the derivative, first derivative test. And so, okay, that's fine. We'll do a t. And if I do the t, opposite that +2 is a 1. So guess what? That's one of my beauties. And this is my x value. My other, aside from the 2, would be the 3, right? And so we throw this into our first derivative. What happens? So let's start with the 1. So -1 divided by 1 minus 2 squared. It's squared. Who cares if it's negative, right? Because it's still going to become a positive. So you still have a negative divided by a positive. Do you agree?
Yeah.
So final answer here is this is negative. And let's do the test for the 3. So if I have -1 over 3 minus 2, who cares? it's whatever it is, it's squared, it's still positive, divided by a negative is still negative. Do you see where we are still agreeing? So in this case, we would say negative infinity to 2 and union 2 comma infinity, we are decreasing. Okay, I'm not doing another try on that one unless you want one. Do you want one? Does anybody want one? No. Okay, example 5 I'm eager to get to. So in example 5, you have to recall your natural log derivatives. Okay, and so here's example 5. Actually, let me switch pages. Example 5. So they're asking for the partition number and critical number. This is for the first derivative, and this is simply for f of x. So f of x is equal to 8 natural log x minus x squared. The first thing we need to do is let's find that first derivative. I'm seeing some people just waiting for me. You ready for me? You ready? So this should have given you 8 over x minus 2x. That's your original result. However, you cannot add two fractions unless you have a common denominator. So this is technically over 1. So you're going to have to multiply this by x, and you're going to have to multiply this by x, which now results in 8 minus 2 x squared all over x. Still not done. While yes, this is your first derivative, you can still factor that, right? If I take out a 2, I'm going to end up with 4 minus x squared over x. I'm still not done. I could still factor that further. This is 2 parentheses, 2 minus x times 2 plus x, and all of this is over x. Just remember, x has to be a number greater than 0. Okay. So I graphed this on Desmos. You have to be careful with Desmos because it's kind of a pain when it comes to natural logs. So in this case, I said f of x is equal to 8 times, you have to select your functions down here. That patience. Natural log. So if you use Desmos, I hope you made note of what I just did. Minus x raised to the second. That's what that looks like. That's your original f of x. If I were to graph the first derivative, let me see if it'll even take it. Where is that little thing? Whatever, I'll call it g of x. And that is simply equal to 8 over x. Look at what's happening in the background. Okay. Where did it go? Oh. Capital minus x squared. Okay. So what's going on here? What is this? What is this madness? Look at that diagram. That's the first derivative. That's what it looks like. So for this one, you notice why we need those critical numbers? Oh yeah. All right. so we're gonna start. With respect to our test points. So if we look at the original question, you can see that 2 is a hotspot, right? So 2 is our, so this is X and this is Y. At 1, 2, 3, 2 is that cutoff number. And you can see that on the graph. If you need, I'll go back. If not, I'll continue. We know that 3 on the money is one of the values, and the other one is an irrational number that goes through here. And so this does this behavior. Going through the origin. Or through 3, not the origin. So if we use partition numbers, let's use 1 as a partition number. So I use the 1 over here, because eventually this is going to cross over. And I could use the 4, 1 and 4, those two numbers. And so here we would sit with x, and this is f of x, f prime x, the derivative. And so I'm going to use 1 and I'm going to use 4. So if I use 1, I have 2 times 2 minus 1 times 2 plus 1 all over 1. So 1 times 2 is 2 times 3 is 6. This is 6 and this is a positive 6 at that. So it's going positive on one side. And actually on the left side of the 2, right? So going this way. On the right side, if we plug in 4 instead, notice I'm changing these to 4s. So you have 2 minus 4, which is negative 2 times 2 is negative 4. Negative 4 times 6 is negative 24. Divided by 4 is negative 6. So negative 6, and this is obviously negative. So now you can say that from 0 to 2, we are increasing, and from 2 to infinity on this side, we are decreasing. Easy or not? Do you think you have this? Yeah? Okay, then one more example and we'll call it a night. Okay, I don't know how I'm going to do this, but I'll do the best I can. They're giving us a graph. It looks like 1, 2, 3, 4, 5. Yeah, so they're giving us a graph. Let me see if I could pull up some graph paper. What's the matter? Question? Issue? You sure? Do you want me to go back? No? Sure? Fine. I should have graph paper. No, a table. I want a file. I don't want that. Insert should be view. Maybe it's view. Graph rows here. Rows. I need graph paper. All right. Can you see the lines on that, or is that too thin?
Very good. I
can barely see it, and you're right in front too. What about this one? Is that any better? That's worse.
I can kind of see the small line.
What about these? Is that better?
It's really just okay. Yeah, now we can see it.
Okay.
It's just the blue, so like.
Does anybody know how to make the lines thicker? I mean, I can draw them out, I guess. Okay, look, you gotta see how cool this is, dude. Like, okay, now back off, cause I'm like totally Mac Daddy cool here. My geekness is like elevated right now, elevated status. Ay, Dios mío. I'll get this like straight up and down. You know, you should see me when I'm drinking. No, I'm kidding. I'm so kidding. I'm so kidding. I don't even drink. I swear. Alright. Alright, here we go. Did she just hear me say that?
No.
Because I'm like, it's in Murphy's Law. You know, once I threw a book in a classroom and the administrator was walking right in. Missed the administrator by like inches. Yeah, my first time teaching, I went to pull down this thing. This used to be one of those old projector style. I ripped the whole thing off the wall. You imagine on your first day and that's the impression you give? Thank God that was 27 years ago. So, we all will fumble in our careers. All right, so the best I can do, okay? All right, I don't want to hear any crying. It's crying is for not for baseball. 1, 2, 3. All right. Okay, I'm gonna come over. 1, 2, 3. All right, 1, 2, 3. I'll put a dot there. Just bear with me for a second. I'm gonna give you a nice clean picture. It's gonna go through 2. It's gonna go through 2. It's gonna hit the bottom here at 1, 2, 3. I'm trying to be a little bit more accurate on this one because there's something I want to point out to you. I'm 2 1/4. And it ends at like here. Okay. So if you can take away the diagram here and appreciate what's happening, then we're in decent shape. It looks like that. This literally the graph they're giving you. They're asking you here, use the graph and this to find the intervals on which f is increasing and those on which f is decreasing. Is there any local maxima or minima? So that's why I kind of made this really annoyingly affirmative that this is x is -1, y is 3, because this point is simply -1, 3.
And that would be a high point, technically?
This is the maxima.
That's max.
Maxima. The minima is down here. And that is at, it looks like 1, 2, 3, 4, 5. So -5, -5, 3 as the maximum. So that's what they're implying for us to sort of discuss. If you notice in this case from negative infinity, left.
Be -5. Because you put it.
I promise you, I passed algebra years ago.
Wait, they don't
Promise you. That's just because I'm counting in reverse, that's all.
I get that.
So negative infinity to -1, that is increasing, right?
Yeah.
And we can argue that from -1 to +3, so from -1 to +3, I'm going to write the positive on purpose, we are decreasing. Would you agree?
Yes.
And from +3 to positive infinity, obviously we are increasing. That's all they need you to know in this example. Okay, so when you go on your Alex or whatever you guys use, Pearson, you're just gonna click. You know how many classes I'm teaching right now? Don't even talk to me. I don't even know where I am. Am I supposed to be here? No, I'm kidding. I'm kidding. I'm kidding. Okay, so that's all they're asking you to understand in example 6. So in Pearson, they're probably going to give you a parabola or a cubic function, and they'll ask you the same question, and you're literally going to check off which areas it's increasing, which areas it's decreasing. That's it. Okay. Okay, I lied to you. I have one more example. Get your money's worth.
Alright.
All right, so all you're going to do in example 7 is you're going to finish example 6 off in theory, right? So example 7, we are locating the local extrema. And they're giving you the function where f of x is equal to x cubed minus minus x squared plus sin x plus 1. So the three things they're asking you to do here is to sort of wrap it up. Find the critical numbers. So I'm just going to put critical numbers of f of x So the critical numbers of f of x in part B, find the local max and min, maximum, minimum. We're almost done. Hang in there. And sketch the graph, which we're going to sketch it using Desmos. So, first thing you want to do is we're going to factor this. You're going to take the first derivative and we're going to factor. So we're going to go f prime x is equal to 3x squared minus 12x plus 9. So that's step 1. Notice that they all are divisible by 3.
Yeah.
So let's factor out the 3. That gives us x squared minus 4x plus 3, does it not?
Yeah.
So that's telling me that this factor will be 3 parentheses x minus 1 times x minus 3. So it looks like your factors are 1, or your critical numbers will be 1 and 3. These are the critical numbers for your function, your original function. So that's where we start. So if you think of a number line, you have a critical number at 1, you have a critical number at 3, and therefore you have negative infinity over here, and you have positive infinity over here. So if I'm checking for test points, I'm going to be lazy. And I'm going to tell you right now, one of my test points is 0. The other test point is going to be 2. And the other lazy test point is going to be 4. So these are the 3 points that I'm going to check. So I'm going to say, okay, well, if this is x, I'm going to test this against my first derivative of x. And so here I go with 0, 2, and 4. So let's plug this into our derivative, which you can use either, believe it or not, it's easier to do this one down here. So 0 minus 1 and 0 minus 3, that's going to give you positive 3 times 3, which is 9. It's positive. Do you see what I did?
Yeah.
It's kind of cheating, but it works. If I use again this, which is the same as this, either one will work. 2 minus 1 is 1, and 2 minus 3 is minus 1. So minus 1 times 1 times 3, that's a negative 3. That's a negative. So it's decreasing here. It's decreasing. It's increasing here. That's one way you can approach it. Okay, and last time, 3 times 4 minus 1, which is 3. 3 times 3 is 9. And 4 minus 3 is 1. This is also positive. And actually a 9 at that too. So it's increasing here as well. So you would say from negative infinity to 1, and from 3 to positive infinity, it's increasing, right? And then you would argue that from 1 to 3, not inclusive, it's decreasing. That's it. So you have a local max here. This is going to be a max point. is your local max, and you know that because of the behavior. And this is your min, because it's decreasing here. This is where it's gonna hit the bottom. This is your, call it min, local min. You want to take a look at the picture real quick, so you can tie the piece together. So where this is where. Alright, so here we go. F of x is equal to x cubed minus 6x raised to the second
Plus 9x.
plus 9x plus 1.
Oh.
Chicken? You see how it's increasing from negative infinity to 1? And then from 1 to 3 it's decreasing. And then again it's increasing from 3 to positive infinity, and you can tell based on the first derivative and its result. Okay, I will finish this chapter with you Wednesday. Wow, I got further than I thought I would. I'm so excited. Little victories, little victories.